Okay, so I guess we can start. Thank you all very much for coming to this late session. I know that's not the favorite slot that you get during ELC. But I decided I could use this opportunity to try something new for me and not use a laptop for giving my talk that's about a virtual computing platform for the Internet of Things, but I'm using a tablet PC, because that's all modern and stuff, so I hope you don't mind being my victims in that experiment. Yeah, I do work for Siemens. We are actually not known as a Linux company per se, but you may have heard this morning that we founded the CIP initiative together with some other industrial companies to take care about long-term maintenance of the Linux kernel. And actually we do invest quite a bit into Linux, and it's running in many products, even if it's not so well known. And I also have a second academic affiliation at the Technical University of Regensburg. So this talk will be a mixture about some crazy academic ideas and how to apply these to future industrial Internet of Things platforms. Okay, skipping slides works. So as I already said, I do work for Siemens. I work on a number of projects, including magnetic resonance scanners, industrial control. That's an X-ray scanner, that's a communication device, and so on. And yeah, I also wrote a number of things about Linux, so the Linux kernel is actually one of my specialties. And we're currently trying to see how far we can get with Linux on Internet of Things class devices. Yeah, I guess I don't need to tell you a whole lot about how the connectedness of devices has evolved during the last couple of decades, starting from mainframes that were actually mostly completely unconnected except with terminals, in the close proximity to desktop PCs that started to become more connected to each other in the 80s with modems and stuff, to mobile systems that are always on. They're always connected to some type of network, but they are not used for doing these heavy calculations that these two classes of PCs were being used for. And these days we've ended up with ubiquitous computing. Basically everyone is carrying around more and more and more computing devices. And in contrast to mobile systems that you still use these days mostly for checking emails, for making the odd phone call, maybe playing a little game or something, that are not so much into computing as such, these ubiquitous computing approaches really need to do more and more heavy data processing, need to do signal evaluation, need to do statistical learning and prediction and so on. So computing actually is getting back very much into mobile systems. The issues, of course, are we are going to have very heterogeneous hardware, so it's completely unclear which future systems will make up the Internet of Things, and manufacturers are currently fighting quite some battles over that, so it's expected that we will end up with lots of variability. We will see the same problems that we saw when cloud computing started off. So we have very high peak requirements when you actually need to do some heavy-duty calculation, like you have a heartbeat sensor, and the sensor needs to detect from the signal it measures if you are going to have a heart attack or something like that in the near future, then it will have quite some substantial loads to process, but most of the time it will be idle. So we will have very high peak requirements, but only a very modest average load. And of course, if we have tons of devices that need to satisfy high peak requirements, but only average load, that means we will have a lot of waste. We will waste a lot of money because there's silicon around that is not used, and that's obviously something we want to avoid. This will get very bad if the predictions for the growth of the Internet of Things will really become true, because we will have billions of devices, and if each of these devices only wastes even a small fraction of their computational capabilities, we will have waste times billions and waste times billions. Even if the waste is small, if you multiply it with billions, it's still going to be quite a lot of waste. So you could say there's a vast amount of computational resources that's lost in Internet of Things type networks. That's the negative way of viewing things. You could also see it positively, and that's what we decided to do. You could say, hey, these computational resources are not lost, they're actually available and just sitting around there and waiting to be utilized. We could utilize these resources for a number of things. I mean, data processing and data analysis. I already mentioned we can use it to build distributed intelligence, like we did in distributed computing. We can use swarm computing approaches and so on. So people will definitely come up with uses for these resources if we manage to leverage these resources. Actually, so where are these resources? I've drawn up this picture. So of course, the Internet of, here we have the cloud with large machines, with server class machines that you can use to offload really demanding computational tasks. Cisco and other companies have begun a couple of years ago to advocate the fog computing approach, where data processing is done on the edge of the network. So these 4 dots are supposed to represent network switches that also have quite some computational power that you can use to offload computational tasks from these individual Internet of Things devices, computational tasks that are not so demanding to require cloud computing, but that are too demanding or that exceed the capabilities of individual IoT nodes. But that, of course, leaves the IoT nodes, these small nodes here, outside of this load distribution. And that's actually the place where we have focused our attentions to. We would also like to combine the computational power that's in the inner circle of the network, so really in the small end devices, because even if these individual devices have much less computational power than the devices used at the network edge or even in the cloud, if you multiply this small computational power by a large amount of devices, you still get quite a lot. So what we envision, what we were trying to do is to build, if you see these boxes represent the individual IoT devices. Red is the amount, the load that's being processed by the devices, and the green part is all the computational cycles that are still available. Load these devices up to 90%, so if the individual devices are fairly well loaded with computational tasks, if you sum up overall these unused green computational resources, and if you manage to combine them into a coherent whole and make them look like a single machine, then our assumption is you will have a lot of computational power at your availability. Good, so what are our requirements? We discussed with some experts in the company and with some external experts to whom we showed our scenario, and we came up with 5 or so requirements that we need to fulfill. The first requirement is, if we want to build such a network, if we want to build such a virtual computing platform, that's clear what I mean with that, and virtual because it's a computing platform that's not built on one single physical device, but on an aggregation of various physical devices into one virtual computing device. One thing that we need to take into account is, of course, we cannot make do with static configurations like that it's mostly used in cloud computing. We don't know that we have, say, 10 servers here, and then we need to push load onto these 10 servers, but we will be dealing with networks that are very dynamically organized, where nodes can join and where nodes can leave basically at will. So we will need to we will need to use means of also integrating new nodes to be able to realize dynamic setups and especially benefit from dynamic resource allocation planning. The nodes will be highly heterogeneous, so they will need to announce their computational capabilities, in terms of how fast they are, what the memory what the available memory, their available storage options are, and so on, but also what load they are currently experiencing. If you want to make a decision where to offload computational tasks, you need to know which loads are currently bored, so to speak. The data, of course, that are being processed must be available across all nodes. I guess that's a requirement that goes without saying, so it's fairly obvious that we have this requirement. One thing that's particularly hard is that we, of course, want to specify programs in modern languages, so languages that have a certain amount of convenience to the programmer. IoT devices these days are very often programmed in C, which is a very low-level language, as you all know, which invites lots of mistakes to be made and things like that. So we want these modern languages, like type-safe languages, like dynamic languages. But usually these abstractions come at a price. So you need a certain size of your computer to accommodate such languages. But we want to benefit from both things. And of course, if we want to realize distributed computing on the level of IoT devices, we will need to have ways of distributing certain computational units among the network. So if we just distribute single functions, then we could as well go with a standard RMI approach, a remote method invocation approach, which has its known drawbacks and especially requires a lot of upfront planning. So you need to really design your systems in a way that you can work with these RMI approaches. So we want units that are a bit larger than a single function that we distribute. We want actually logical computational tasks to be distributed, but these logical computational tasks will also be smaller than complete programs, so we're not intending to shift around whole applications in the network, but just the things that really matter, and do this in a very dynamic manner. So basically, to sum up what I'm just described in a picture, what we would like to have is, if we, for the sake of simplicity, say we have a system, or we have two IoT class systems, system 1 and system 2, where one of the systems is currently experiencing very high load but wants to do some computationally intensive task, then we basically want to shift the code that is responsible for performing this computation, be that a single function, be that a couple of functions, be that maybe some library or whatnot that you need to call. We want to shift this code to another system that is currently not experiencing any high load, so that has time, so to speak, and do the same computation. And we want to do this transparently, so we want both systems, the combination of these two systems, to act like one single big virtual system. In an ideal case, we'd even want the programmer to not notice this. That's, I guess, not something that we can achieve very easily, but it should at least be not visible to the end user. Good, so since the Internet of Things is still a very imprecisely defined term, let me make a brief detour to explain what I understand by Internet of System class devices. So I find it useful to classify systems by the power consumption, because that gives a fairly nice hierarchy. So we have these very small systems that consume less than 1 watt of power, that have less than 100 megahertz of CPU frequency, less than 10 megabytes of RAM. So really small systems like Arduinos that are used as embedded sensors or as wearables. So this is not what I'm talking about, because if you're dealing with such small machines, then your options typically are so limited in terms of computational capabilities that even if the systems are complete without any load, it doesn't really make sense to offload anything to these systems. What we are interested in our approach is the class from 1 to 5 watts that has that consumes 1 to 5 watts of power, that has maybe a CPU with 1 gigahertz, 1 gigabyte of RAM, maybe some external flash. So that's nothing that would really impress your neighbor as a supercomputer, but that's if taken in if available in large quantities, is something that can actually achieve quite a lot. And if you think 10 years back, I guess that already would have been a dream system to do many computations on. So that's machines of the class Raspberry Pi, Banana Pi, and so on, and that is the class of machines that we are focusing on. Of course, the larger machines, 5 to 50 watts, like the Jetson TK1, may also benefit from such an approach, but we're more focusing on that, and anything that has more than 50 watts, we do consider like a server computer. Good, so the nice thing about this classification is that it maps fairly well also to the type of connectivity that the systems usually have. So if you consider these very small systems, these systems from 1 to 5 watts, okay, so that's the tablet experiment. That went wrong, that went very wrong. But I'm getting back. I have an empty slide. So that's the slide I wanted. Great, so I still need to train me to do that properly. So the class with less than 1 watt is what many people would consider core IoT systems that have only local connectivity, local wireless connectivity, that are typically programmed in C and that do fixed jobs. So what we are looking at is one level above these very small devices. These tiny devices, they are still small, but they're not doing any fixed jobs, so they are processing variable computational blocks. They're not processing complete apps, or they are not processing complete machine images like you do in the cloud, but they're doing more than just simple fixed jobs. So this is the class that has wireless and wired connection, but doesn't use any specialized protocols, but makes do with standard TCP/IP, IPv4, IPv6 protocols. Good, so when we tried to build such a system, we actually wanted to reuse as much of the existing technology as possible. And requirements I outlined are not completely off what we use in cloud computing. So we did consider if we couldn't use elements of OpenStack and similar approaches and adapt these to our needs. Of course, things like Azure or the Amazon Elastic Cloud are obviously out of the picture when you're using a Raspberry Pi. But initially, we were hoping to maybe benefit from OpenStack. We did try that. And amazingly, we learned that using OpenStack on Raspberry Pi machines beyond a simple demo setup is a really good way of frying up your Pi. So we've experienced so many hardware defects and broken boards, it was not really fun. Of course, if you're really into this cloud stuff, cloud type computational approaches, then you also need hardware virtualization. That's crucial for most of the even open source approaches, and that you don't have in many of the small systems that I described. Why did we not reuse existing technology for distributed computation, like approaches like Apache Spark, or distributed file systems, distributed processing mechanisms like Hadoop, or well-introduced mechanisms like COBA and RMI. We also did experiments with these, and it turned out that, say, Apache Spark is much more suited to be run on a network of Raspberry Pis. It doesn't fry them, so it seems to have less stringent requirements on the hardware. But again, we spent most of the time executing the whole infrastructure instead of doing any computational tasks. So the resource requirements were did quite exceed what we had reasonably available. So these two things did not really work, so we decided to try to build something that was based on existing technologies. But yeah, that was that was something new, so to speak, and I'm going to present that now. Our assumption that we did when we chose technologies was that, of course, Linux will be the most widespread operating system on the class of devices I described, but we wanted to keep the possibility and the option of maybe going back to RTEMs, going back to FreeRTOS, because it turns out that the Linux kernel as such provides a lot of functionality that you really don't need in this class of systems, and if you go with lesser known approaches like the two I mentioned here, you still get most of what you actually do need. So we didn't want to introduce anything Linux specific, and we actually also did all our experiments with RTEMs and not just with Linux. Yeah, the additive or subtractive engineering question, that just means, should we take something and some existing code and extend that with functionality that we needed, or should we take bigger systems like OpenStack and strip them down to be of appropriate size? We decided to go with an additive approach because it turned out to be easier to add stuff than to make all these huge existing approaches smaller, because I don't know why the cloud people and the distributed computing people always go for such large systems, but whatever we tried was really so large that it would have been much more effort to strip it down than to write it completely from scratch. And of course, I said we wanted to use dynamic and interpreted languages to benefit from their advantages, but which language should we choose? Okay, so as for the capability discovery that I mentioned here, the solution was really easy. I said we made the assumption that we will be using TCP standard TCP IP networking, and to generate networked systems without any central server components that work in a dynamic fashion, you already have all technology available. For address assignment, you use IPv4 low-level link local addressing, where systems basically agree on their IP addresses without any central instance like a DHCP server. For name resolution, we used multicast DNS that allows us to resolve symbolic names into IP addresses without having to resort to a central DNS server. Also suppose you all know that. And to announce the capabilities, the computational capabilities of the individual devices, we use DNS SD. That's a technique, basically to send information about systems via the DNS protocol, via the DNS extensions of the DNS protocol. Since we did not only want to support Linux, but we also wanted to support smaller systems, we needed to look into which implementation to use. And basically, there's 4 variants available. That's Avahi, which is the standard MDNS, DNS, SD implementation on Linux systems, which is actually a fairly complex code basis. So it's not like Mozilla's Firefox, or it's not like the Linux kernel, but still for such a small dedicated job, it introduces quite some code into your system. But it's a very mature implementation, so it's basically used on any standard Linux installation. The alternative to Avahi is Bonjour from the Apple world, so the original Apple implementation of the protocol. Apple also did the specs. Basically supports the same things as Avahi does, but has, in my opinion, nicer implementation, so it's less complex, it uses less Linux-specific things, and is also available under a license that you may arguably find more appropriate for IoT-type systems. We also tried OpenMDNS and Tiny SCMDNS, but these do lack capabilities that we needed, so we didn't consider these approaches any further. Actually, we focused on Bonjour because it turned out to be much easier to port to RTEMs than Avahi, but provides actually the very same functionalities. Good, so as for the language, we decided to choose JavaScript, as I said already in the title of the talk. And that really raises some questions. So why did we focus on JavaScript? We also tried many languages. We experimented with Lua, with Python, and many other languages from this class. But JavaScript, although it is a very odd language, not a very clean, a very nice language, has some advantages that are really intriguing. And these advantages are basically, so these days you can use JavaScript as a target language that is output by several compilers, including LLVM. So if you don't like to write JavaScript code, you basically take any language or languages that you like better and find a compiler that outputs JavaScript for you. That's one of the nice side effects of the web and the ubiquitous use of JavaScript on the web, that you can find compilers that basically translate everything to JavaScript. And the second advantage is really performance. So people have spent so much effort to optimize JavaScript, it's not really funny, because they just need to build efficient web browsers, and all this effort that was spent on optimizing web browsers and that was spent on optimizing the JavaScript just-in-time compilers on web browsers, we can reuse on IoT systems. Of course, you also have the advantage that you're able to generate code on the fly as with every other dynamic language, but that's more a side effect. Now, I don't really like JavaScript as a language, and it is a very wouldn't say bad, but it's just not a nice language to write code. But you need to think of JavaScript in our context not as a programming language, but really more of a new form of assembly language. So it's something that you generate, it's something that you don't write by hand. That's also the approach that the web people have taken with TypeScript, with CoffeeScript, and so on. So you have these nicer languages, and then you just transpile them into JavaScript. That is then used not as a programming language, but as an assembly replacement, with, of course, the advantage that you don't need to care about which system you're running on, whether you're running on an x86 or an ARM or a PowerPC or whatnot. It's just a JavaScript interpreter for you. Good, so our concept that we are using to distribute computational load across systems is very simple. We have machines that are connected by standard Ethernet, by standard TCP/IP connection. And on each of these machines, we have a daemon running that is responsible for distributing computational load across systems. So these daemons know what systems are available in the network, what the current load is, and so on. It's all being done with the technologies I outlined before. All we need to do is write our programs in some language that can be transpiled into JavaScript, and then mark regions in these programs that can possibly be outsourced. Like, we do that on the function level, but we also take into account that these functions may call other functions may have library requirements, and so on. That's noted, and then we get these computational blocks, these computational entities that we can shift around. And instead of calling the functions directly locally, we're making a request to the daemon to execute this piece of code for us, and then the daemon decides, should I execute it on a local machine, depending on its load, or should I move it to some place else in the network? So as for the parameters and the results, we are using very simple JSON strings, also standard technologies, to encode what we give as parameters to the functions and what we get back as results. So we don't need any complicated CORBA or other RMI mumbo jumbo to do that. It's really very simple, which is good because simple is, of course, good. We distinguish between three different methods of passing on the code that we want to execute. And one thing is we can use local storage, so we can say if we know more about the system we are operating on, we can pre-distribute the code to the local storage of the systems, which of course requires some storage space on each system, but has the advantage that you don't need to do any network communication to distribute the code. We can use network file systems to store code in one central place. Has the disadvantage that you have a single point of failure, has the advantage that you can cache stuff, or we can use a completely dynamic dispatch where you actually transmit the code that you do want to execute together with the request to execute that code, which is of course the most dynamic and the most flexible option, but requires more resources in terms of networking. Good, again, so the way how we distribute that is very simple. I've presented a JSON example, what we send here, but I guess that's nothing spectacular to talk about. As for the network file system, we did a very comprehensive evaluation what could be the best technology for the class of system that I described. So we covered everything from SSHFS to distributed hash tables like Cordelia. I'm not going to discuss this table in detail because I think it's more or less self-explanatory. What we found is that incidentally SSHFS and the 9P file system were best for our purposes because they have very low to very low resource requirements. They don't require any dedicated server setups, but they do support most things that you desire. And actually, we used SSHFS as a networking file system, and we really like this choice up to today because we didn't see any drawbacks, and it's a very simple system to use, and it has basically all the advantages of a network file system that you like, but it doesn't come with the complexities of network file systems like NFS. So we're using Node.js to handle all the JavaScript, which is basically Google V8 plus some libraries. And we did run the tests that I'm presenting, we did run on Raspberry Pis and Banana Pis. So is our approach sucks? I'm going to skip over that. Basically, these slides just tell you that the SSH overhead is very little if you are transmitting large portions of code, large portions of information. So you get around 10% overhead compared to a raw transmission of the data. What was a bit astonishing that you have very many options in SSHFS in terms of compressed transmission, uncompressed transmission, which compression algorithm or which other algorithms you want to use, but it doesn't really make any difference which settings you choose. That was astonishing because I thought there would be some reason behind all these settings, but turns out there isn't. It doesn't really make any difference. What's more interesting is the temporal overhead that we're seeing and the overhead of the different remote processing options. So here we were comparing different ways of storing the code, so storing it locally on the device, using an explicit transmission of the code each time we execute it, and using networked file systems, or the SSH file system. So what you see here is basically, and we use that for different input sizes, 3 orders of magnitude. So input size 1, say 1 kilobyte, 10 kilobytes, and 100 kilobytes. Of course, the execution time goes up, but it's actually a very favorable scaling. So it doesn't really matter much how large your input is. It's the execution time between 100 kilobyte input and a 1 kilobyte input with an algorithm of linear time complexity varies between 800 milliseconds and 600 milliseconds. So actually most of the additional network load is basically doesn't make any difference. So the execution time overhead for local and remote execution. So I'm comparing here local execution, so that's on the 0 line, so you don't see anything. Of course, we don't have any overhead for remote execution when we execute locally, but the different overheads that we observed in our scheme are astonishingly little. So when we store the code locally on the remote system, so the code we're executing is already there, we're just sending a request to execute that code, that generates a overhead of about 1 millisecond, which is very little. If you are transmitting the code via the network file system, you're seeing slightly more overhead, like in the 3 millisecond range. The first call is actually more expensive because the code needs to flow from the host to the client, but then the caching mechanisms of SSHFS basically eliminate that overhead for you. And even if you send the code directly, so from node A to node B, then the overhead we observed with reasonable transmitted code sizes like 40 kilobytes, and 40 kilobytes is already quite something. So you can do a lot in 40 kilobytes of JavaScript, only go up to 25 millisecond remote execution compared to local execution. And that is quite encouraging. These are quite encouraging numbers, because if you consider standard technologies like Java remote method invocation, they have typical overheads of 800 microseconds, but that's for a single procedure call, whereas we have overheads of 1 millisecond if we pre-distribute the code, which is a fair comparison against RMI, because in this case, you also need to have distributed your code beforehand. But we have, of course, much more options in our scenario than with a fixed remote method invocation procedure. So that works fairly well. The main problem that we are seeing, or that we were observing, is how to make the decision when to offload code and when to keep execution local. Actually, we thought that would be a very, very simple problem. You just measure the local load level on a single node and then decide from a certain threshold on and from a certain information you have about how much computational time your code needs. You compare that with the load level of other systems and then make this decision. But we've been spending quite a lot of time on finding appropriate ways of simulating load on such systems. So that is one particular test that we wrote. So this is a program that basically uses up CPU cycles for a configurable, that is such a hard word, amount of time, ranging from 0% of the CPU time to 95% of the CPU time. The problem we are having with that approach is that the variance increases very much in terms of wall time, execution time. So, and that's why it's very hard to make this decision when to offload or not, because it's basically a game of chance. So if you end up in this scenario, where the system load really induces quite a long waiting time, you better offload your code. But you can also observe a system load value of 95 or 90 and be in this portion, and then you would have better executed the code locally. That didn't get better when we switched to different types of generating loads. Of the previously shown measurement was with custom code. This was just using the standard Linux stress utility that it basically hogs one single CPU 100% of the time. So we were using a banana Pi machine, which had like did it have 4 cores? Yeah, I think it had 4 cores, makes sense. So if you use up half of the system's resources, like 2 CPUs, basically you don't see any difference in execution times. When you start using the third CPU, then there is one CPU still available, more or less exclusively for your load, but you have to handle then system tasks and periodic daemons on that CPU, so the variance increases, and only when you really use up all 4 CPUs, you see a substantial increase in execution time for your system. But although this measurement should more or less represent the same scenario as the measurement before, like from 0 load to 100% load, you see that the outcomes are quite different. And so that's conclusion is that it's very hard to say something meaningful about the real load of a system by just observing this single number. Nonetheless, without going into any of the details, so I'm finished in like 4 minutes. That's good, okay, perfect. We came up with after doing lots and lots of tests and spending many CPU cycles on trying to connect load levels with actual system load, we came up with a probabilistic or a stochastic model using some advanced linear regression that gives us an indicator of when to offload or not. So it's still a game of chance. It may make a decision to offload when it would have been better to do the computation locally, but our results so far indicate that we are right, say, most of the time without going into any of the statistical details. Actually, what we found out is that 3 things are good predictors for offloading computational load. That's the code and data size, so size of code that we offload and size of parameters that we offload, and the scaling behavior of the algorithm. So is it a linear, is it a n squared, an n log n, and so on algorithm? These 3 covariables are good predictors. What astonishingly has no predictive value at all is the network load. But if you think about that for a while, you see that 100 megabit per second network is basically so fast that these 40 or 50 kilobytes of code that you are distributing don't make any real load on the network, which is, I guess, a good thing. Okay, so coming to the conclusion, we used an unusual approach to build a virtual machine out of a network of Banana Pi or Raspberry Pi class devices that relies on JavaScript to exclusively do all or express all computational tasks, computational blocks. It has similar overhead to standard RMI mechanisms. It's much less complicated than most of the RMI mechanisms, at least the mechanisms I know of, but we have considerably more flexibility in our approach. I think because we can offload a much larger class of computational blocks than you're able to with standard RMI. So we think that's a fairly good option to explore further in the future. If you want to play around with what I just described, we haven't published the code yet, but the OSS publication is upcoming, and I guess we will have done that like in 4 or 6 weeks. So this will all be available to play with for you. Good, that's all I wanted to tell you. If you have any questions, then fire away. If you have no questions, I do again, no, there are questions, great.
Does it take care of like when you offload a task and the other node dies? And then also there's some coordination so that if I decide I would offload the work to this node, right? Another node will also decide to offload their work to that node, and they kind of collide, overload it.
Yeah, actually, we thought about using a mechanism to provide mutual exclusion to avoid this situation, but then in the tests we realized that this basically never or only very rarely happens, that 2 nodes at the same time decide to offload things to another node. And since our decision when to offload stuff is stochastic only anyway, we figured it doesn't really make sense to build a mutual exclusion protocol into our system. We could do that, of course, very easily if we had a base file system that would support locks, which SSHFS doesn't. So we figured we just live with that risk. That's another stochastic thing, but it doesn't really matter to us.
Then, 9PFS, it looks like from your table that you tested.
9PFS does support that. And in theory, it would have been the better choice, so it had more like green check marks. But it turned out that the implementation is not that great. So we experienced many, say, Heisenberg bug or Heisenberg type bugs that we couldn't really reproduce. And so we decided to switch to SSHFS. 9PFS, if someone would really take care of bringing or optimizing the Linux implementation and bringing that into a good shape, would also be a very good candidate. And it actually has been used for this class of systems by, I forget the name of the paper. It's a paper from like 5 or 6 years ago. They used 9PFS for very similar purposes, so it surely would be possible.
When you said the predictors, better predictors for the code size of the data set,
Mm-hmm.
So you predicted what you wanted to upload? So what you wanted to upload, if it was large enough or if it was small enough, that's where, how did you predict when it's better to upload?
So basically, we just took a lot of measurements, and these measurements know that we are now executing a code portion that's maybe 20 kilobytes of JavaScript and say 300 bytes of parameters. And then it's a binary decision, offload or don't offload. And we just used the standard statistical approaches, measure a lot of data, then see when it would have made sense to offload and when not, and then train a model.
Yeah, so did you find that offloading larger pieces of code with larger data chunks was better, or the other way around, smaller pieces? Or was there just a sweet spot in there?
Actually, we are still looking for the sweet spot because it's not completely, but it's quite astonishing for how large a region of parameters it makes sense to offload. So I would have expected that we would see a cutoff somewhere. So say when we have more than 50 or 100 or something kilobytes of code, but the networks are so fast these days. And the JavaScript just-in-time compilers are also so fast these days that basically we did lots of measurements and we did offload megabytes of data, but we didn't reach a cutoff point. And so we just focused on the smaller things when the overhead, I should be able to go back somewhere here. So when you look at this slide, basically, when you look at this slide, so the overhead of SSHFS is negligible for fairly large transmission sizes, but it becomes very, very substantial when you go into regions of 10 payload bytes or 100 payload bytes. Then you have like huge overheads, and this is the region where it doesn't make sense to offload stuff, but that again is more or less common sense, because if you're offloading like a 2-byte call, then it's clear that this won't work. Okay. Good. So,
have you heard of folding at home?
folding at home, so that's this biochemical thing.
Yeah, it's Stanford University.
Protein folding, yeah.
Yeah, we've been donating unused time on our computers
Mm-hmm.
for about 15 years to them.
Mm-hmm.
So
Yeah, it's the same thing as like SETI at home and all these other approaches, but I think they are, okay, so I'm getting the red flag. I think they are dealing with a different situation where they are executing a very specific piece of code and the loads don't vary. Okay, so thanks despite me talking a minute too long.